Okay, why don't we get started? So, hello everyone, and thank you for joining us. Welcome to this presentation, which is part of an ongoing Goose webinar series looking at issues and projects associated with global sustained ocean observing. My name is Albert Fisher. I'm the director of the Global Ocean Observing System Program Office, which is headquartered at the Intergovernmental Oceanographic Commission of UNESCO in Paris. And for the next hour, we'll start with an approximately 30-minute presentation from Ken Johnson and Herve Claustre, who are the co-chairs of the Biogeochemical Argo Steering Committee. Ken is based at the Monterey Bay Aquarium Research Institute and Herve at the Laboratoire d'Oceanographie de Villefranche in France. So biogeochemical Argo is the extension of the Argo array of profiling floats that include floats equipped with biogeochemical sensors for 6 essential ocean variables, in addition to the temperature and salinity sensors carried on core Argo profiling floats. After Ken and Herve's presentation, we'll conduct a question and answer session by chat. I'll moderate and select and ask the questions verbally. The chat window is open right now, so if you'd like to start asking clarifying questions, please feel free to go ahead. The session's being recorded, and a link to the recording will be posted on the Goose webpage. So Ken and Herve, let me turn it over to you for the presentation.
Okay, Albert, am I on?
You are indeed, so go ahead.
Okay, thank you very much. Thank you, Albert, for the invitation to present. As Albert said, we're going to talk about the prospects and rationale for a global biogeochemical Argo system, or BGC Argo. This is a joint presentation by myself and Herve Claustre. On this opening slide, I've put the icons of the groups that have funded our work, and I have neglected to put on Herve's support. I don't know, Herve, do you want to say something about the groups that have supported your work as well, or should we just get into it?
Go into it. It's okay.
Okay. So as Albert pointed out, biogeochemical Argo is the extension of the Argo array to include profiling floats with biogeochemical sensors for pH, oxygen, nitrate. Now, and I have lost, did you do that, Albert? I can't see the screen. Yeah, okay, there we go. Did I do that or you? That include sensors for pH, oxygen, nitrate, chlorophyll, suspended particles, and downwelling irradiance. There's real-time public access to the data, just as with Argo, so data goes onto the internet in real time, and BGC Argo floats generally follow the Argo mission, that is 1,000-meter parking depth, a 5 to 10-day cycle time, and then profiling from about 2,000 meters to the surface. There are exceptions in core Argo, there are exceptions in BGC Argo in the operational, but in general, it's following the Argo mission with the goal to get interannual, seasonal interannual cycles in these 6 variables, which are all essential ocean variables, essential climate variables of one type or another. So I just want to make the point that BGC Argo is an active program right now. There are about, as you'll see, about 300 profiling floats in the water today, but primarily these are acting as independent programs by a variety of different scientists, and this talk is focused on the status and planning for an integrated international program. And just to make the point that there are floats in the water, I've put one example of a float from a program that we're involved with, SOCOM, the Southern Ocean Carbon and Climate Observations and Modeling Program. This is a float that's operated for 2 years in the South Atlantic in the seasonal ice zone, and you see the temperatures getting down to minus 1.8. Three seasonal cycles of backscatter, chlorophyll, the oxygen in each spring, the nitrate drawdown each spring, summer season, and the pH increasing each year as the phytoplankton grow. Just to make the point that floats are out there and operating. So the general outline for the talk today is the need for a global biogeochemical observing system, a bit about the actual core Argo observing system and the successes it's had, and address the question, are we ready now for BGC Argo? and then the actual planning for the integrated international program. And throughout the talk, we will have a variety of examples of profiling float data. So, I'm not going to um, belabor the point that there are potential for tremendous changes in the oceans. This is a cover from a special issue of Science on changes in the seas. But I think we generally agree the oceans are undergoing remarkable stresses. Warming, acidification, changes in nutrient supply due to changes in ocean circulation, loss of ice at high latitudes, changing circulation due to winds and heat changes. And the question I would ask is who's looking really systematically at these in the interior of the ocean? And a distressing fact in terms of the fact we believe the oceans are undergoing remarkable stresses. If you look at the statistics for ocean sampling, there's been a remarkable decline in ship-based profiles. This is a figure from World Ocean Database 2013 showing the total number of ship casts per year that are found in the database. Starts in the year 1900, runs right up until 2013. And since the late 1980s and 90s, there's been a precipitous decline in the number of ship-based profiles. For temperature and salinity, this has been primarily offset by the Argo array, as we'll see, but not the case for biogeochemistry. If I go back again to the World Ocean Database and ask for the number of oxygen profiles to a depth of at least 900 meters, these are the number of profiles per year. Again, there was a maximum back in the 80s and 90s, and the number of profiles per year that are going into the database is now roughly a quarter to a sixth of what it was back in the 80s and 90s. If we're concerned about processes like ocean deoxygenation, we're not sampling it very well. So, that's basically all I'm going to say about the need for a global observing system. But this is generally true for a variety of processes. We need to step up our observing. Existing systems are not filling the need. In the case of the declining number of shipboard observations, let's see how Argo has stepped up to address that problem. And so most of you are probably familiar with figures like this. This is the Argo array as it stands in the ocean this month. Almost 4,000 operating floats, 30 plus nations deploying the floats. So each dot is colored by the nation that has deployed the floats. Remarkable coverage over the world ocean. And the program has been an incredible success. If you want a summary of the work that's been done, I'd recommend this recent paper by Steve Reiser et al., 15 years of ocean observations with the Argo array, and to see the direct science impacts, this article by Dean Remick et al., Unabated Planetary Warming in its Ocean Structure. The inset figure here is from the Remick et al. Paper and shows the warming resolved by latitude bands. Interestingly, most of the warming in the ocean one would find in the 60 south to 20 south band, and relatively less warming elsewhere. They're able to, well, let's see, I'm going to go back and just make the point, in case anyone is not familiar, the inset shows the typical Argo mission profile here. So profiling float, modern float will spend about 15 minutes at the surface to send data. It descends to 1,000 meters, drifts for 5 to 9 days, then descends to 2,000 meters and rises to the surface, collecting data on the ascent, and again telemeters its data to Iridium satellites, and data is immediately available on the internet. So Argo has been so successful because it has basically, really transformed global scale oceanography into global oceanography. This is a figure that was prepared by Howard Freeland, the Argo executive director. Top panel shows the number of profiles returned by Argo. There are now about 1,450,000 temperature and salinity profiles from 1999 to 2015. The color scale is the number of profiles per 1 degree bin. We have tremendous global coverage, uh, complete over the world ocean. The lower panel shows what 140 years of shipboard observations have accumulated. There are about 500,000 temperature and salinity profiles to 1,000 meters. Large areas of the ocean still unsampled. Large areas of the ocean where the color scale shows there are only 1 to 5 vertical profiles for temperature and salinity per 1 degree band. Like to make the point that Argo floats operate year round. They don't mind bad weather. This is 5 years of August temperature and salinity profile data from 2008 to 12 from Argo, showing the tremendous coverage. The same ship set of coverage from ships for a 50-year period compared to the 5-year period up here. And last point, World Ocean Circulation Experiment was a global survey of 8,000 temperature and salinity profiles in 7 years. Argo does 12,000 temperature and salinity profiles every month. That this kind of tremendous coverage with uniform spatial coverage, uniform coverage through summer, winter, fall, and spring has allowed Argo to attain this incredibly detailed picture of ocean heat uptake and a whole variety of other processes. There are now a set of biogeochemical sensors that are available and that operate on profiling floats. And basically, for the remainder of this talk, we're going to argue that we're ready to do for biogeochemistry the same thing that Argo has done. And in the face of the declining number of shipboard observations, we can replace them with a set of highly calibrated autonomous observations. So a variety of profiling floats are being launched. We see example with biogeochemical sensors. Here is a Navis float, a Provor float, and the end of an Apex float. These floats equipped with pH sensors, nitrate sensors, oxygen sensors, biooptical sensors for chlorophyll and backscatter by particle, and downwelling irradiance by light, all essential ocean variables that form a key set of observations that allow us to understand ocean metabolism. So are we ready? We're deploying floats. Are we ready for an integrated global program? And so the first point I'd make is that there are a large number of floats now operating in the ocean. This is again from this month from a plot from JCOM Ops of the biogeochemical sensors that are in the ocean. There are 257 oxygen sensors, 75 pH sensors, downwelling irradiance 44, suspended particles 132, nitrate nearly 100, and so on, with relatively, in every region of the ocean from the Antarctic to the Nordic seas, and being deployed again by 15 different nations. So with that data set that's now coming back, much like Argo has become the dominant source for temperature and salinity, not so well appreciated, but BGC Argo is now becoming the dominant source of deep ocean biogeochemical data. If we look at the number of ship profiles per year in the period from 2001 to 2010 that reached at least 900 meters, which would be the bottom of the oxygen minimum, there are on average 1,700 shipboard profiles a year going into the World Ocean Database. Profiling floats are putting 11,000 profiles into the Argo Global Data Assembly Center in 2016. That's 6 times more profiles than ships have done. Similarly for nitrate, there are about 3 times more profiles. For direct observations of pH, profiling floats are putting 4 times more profiles into global databases than ships are doing. I'm not going to belabor the point too much, but this data is highly calibrated and is of a quality comparable to what we can attain from ships. So there's been an extensive amount of planning for global programs. Began with a workshop that was held here at Mabari back in 2009, observing biogeochemical cycles at global scales with profiling floats and gliders. That was an OCB scoping workshop with international attendance. There's been a IOCCG working group looking at bio-optical sensors on Argo floats. There have been a number of Ocean OBS. There were a number of Ocean OBS '09 community white papers adding oxygen to Argo, bio-optical profiling floats. There has been a SCORE working group that's been incredibly successful, quality control procedures for oxygen and other biogeochemical sensors on floats and gliders that have led up. These programs have pointed towards the development of a global program, but I think a common denominator in all of them is that there's a need for regional programs first as a step before we go to global programs, and those have been implemented. There are a number of reasonably large scale regional programs now operating in the North Atlantic, in the Mediterranean, in the Southern Ocean, the SOCOM program, the Australia-India Joint Indian Ocean Bio-Argo program, and the S1 Inbox program, which doesn't show many floats here. The program's over, but if you were to go to Journal of Marine Research in 2016, you'd see the summary papers from this program. Uh, these programs are being incredibly successful. They're developing, in particular, an efficient data management system that allows us to take the float data, um, uh, efficiently quality control it, determine its accuracy, put the data into the Argo system in a way that other people can access it. It's becoming well documented, so uh, uh, many many of the parameters, for example, oxygen, there is a well-documented doc procedure and document that describes how to process the oxygen data, how to quality control it, how to delayed mode quality control it, nitrate. The basic documents are there, and research papers are being written now on the real-time quality control. But we're doing the proper documentation. The key in all of this is to rely on papers published in the peer-reviewed literature, and that is happening for all of these sensors. A great example is oxygen. So the oxygen data that first went into the Argo system was not the best quality, but there was a tremendous effort by the community to understand how to make that data high quality. It led to a series of papers, an understanding that we could calibrate the sensors when the floats came to the surface by making measurements in air. And that basically has become, the atmosphere has become the standard for Argo oxygen measurements now. A series of papers were written by this, accurate oxygen measurements and floats using in situ air calibration by Steve Emerson's group, our group, air oxygen calibration of oxygen optodes. And this was all pioneered by Arne Kortzinger's group back to the first papers on oxygen on floats, but tackling oxygen optode drift. And I will argue, we have argued in this paper 2 years ago that in fact the oxygen data from profiling floats is now of a quality comparable to the shipboard measurements. But the ultimate assessment of readiness is really the research papers that get published. And I'll direct you to the Argo Biogeochemical Argo Program webpage in a bit, but you see the URL up here, and you can find a bibliography of papers on profiling floats on that website. There are over 100 papers now that have been written using profiling float data that document the quality and the kinds of science that can be done with this data. I'll just give you a quick run through some of these. For example, a paper with 7 calendar years, 12 float years of nitrate data near Ocean Station Papa. The dots are the time series from the Canadian Line P program, and the lines are profiling float nitrate data down here, temperature, nitrate, and oxygen saturation. Paper in Global Biogeochemical Cycles. Herve's group have a phenomenal paper in the Mediterranean Sea looking at the interaction of deep mixing. The blue line is the depth, the mixed layer depth in the Mediterranean, getting down to nearly 1,000 meters, and the injection of nutrients into the upper ocean of the Mediterranean, and the phenomenal phytoplankton blooms that come after that. Um, Giorgio Dal Olmo et al. And have a very nice paper looking at carbon export by small particles in the Norwegian Sea using profiling float data. Um, Steve Reiser's group, Tyler Hennon, a graduate student in that group, wrote a beautiful paper looking at the global array of oxygen floats, 112 floats, and looking at the the twilight zone cycles in oxygen, and which you see here for one particular float, 4 years of data, um, where you can actually observe the respiration of particles as they sink from the surface and consume oxygen, and you can use that to look at carbon export globally with profiling floats. Um, One of the key points that we have learned in these regional programs as we head towards a global program is that BGC Argo has to work in synergy with other components of the global observing system. Has to work closely with the satellites, with ships, with mooring programs. And this is happening. We're learning from the regional programs. This is an example from Herve's group, a global set of profiling floats equipped with downwelling light sensors that allow us to directly observe the attenuation of light in the ocean, and online data that you can access here that compare what the floats see with direct measurements to the estimates from satellites, and you see a bias in the data. And we're learning, we're going to be able to use the profiling floats to correct these biases and generate improved satellite products. An example from work we've done, the synergy between Go Ship programs. So this diagonal line is the Go Ship P16S line, which was occupied in 2014. The pH measurements down to 1,000 meters measured by the ship. As the ship proceeded north from the ice edge, it dropped off profiling floats, and these floats have been calibrated back in to be consistent with the Go Ship data, and then extend the Go Ship time series out in time up to the present. And so we can take the one-time snapshots from the ship and look at the full seasonal cycles, the interannual variability between years along the ship. And so there will be tremendous opportunities for synergy between programs like Go Ship and Biogeochemical Argo. Tremendous synergies with programs underway mapping of surface CO2, the SOCAT, Surface Ocean CO2 Atlas program. This is a paper that just appeared in Global Biogeochemical Cycles, using the pH on profiling floats to compute PCO2 and comparing that to climatologies derived from either the SOCAT dataset or the Takahashi dataset, and looking at the variability. So the points with error bars are the profiling float individual measurements in a region of the ocean where there are almost no shipboard observations, and compared to the climatologies from Takahashi and the Landschutzer time series, showing tremendous agreement in the system, but also tremendous agreement in the summer when there's lots of data, and significant disagreement in the winter when there's almost no shipboard data. So the climatologies can be significantly improved by merging them with the shipboard data, with the profiling float data, excuse me. And so those floats, those examples all come. This is the summary of where we have underway shipboard data for PCO2, colored by the number of months of year where we have data. In the Southern Ocean, there are vast areas where there is no shipboard data, and where there is shipboard data, we typically may only have 1 month covered in the whole over 50 years from from 1970 to 2011, there have only been 1 or 2 months in most areas sampled. The profiling floats now give us the annual cycle and will allow us to tie the very high quality shipboard data into the float data, which provides us the yearly view. So oh, and then I just want to make the point, all of these regional programs have been extremely active in outreach. This is an example from the SOCOM program. They all tend to, many of these programs tend to run adopt-a-float programs pioneered by Herve's group in France. This is a tweet of a float. It's been named Darwin. Named by the Passaic Valley High School class. And here is a picture of students with a model BGC float, and they're doing their homework assignments, studying the profiling float. We provide the data in an easily accessible format for these classes. It's a simple HTML web page. They can go point and click and find their float Darwin and look at the temperature and salinity and oxygen and pH and nitrate cycles that the float is returning. So the actual planning now that is now ongoing for the Integrated International Biogeochemical Argo program. The Argo Steering Team Meeting 15, AST 15, the Biogeochemical Argo Task Team was given a set of tasks, and primary was to develop and update a BGC Argo science plan that incorporated the regional pilot projects and aim towards the global network and develop an implementation plan for that system. And in order to accomplish that, a meeting was held a year ago, January, in Villefranche-sur-Mer with representatives from 8 nations to develop a science and implementation plan for BGC Argo. These are the attendees at the meeting. We tried to have a diversity of career levels, of international experience, and so on. So we had a very broad perspective, a reasonably small group, though, to be efficient in planning. And that group has developed a biogeochemical Argo science and implementation plan, a draft plan, which went out to the community for review, and we then incorporated the comments. You can find that science and implementation plan on the Biogeochemical Argo website, biogeochemical-argo.org. And what you find in the document is that there are 3 major science questions, research topics that a global array will be focused on. One is ocean carbon uptake. 2, oxygen minimum zones and the associated nitrogen cycling that occurs in oxygen minimum zones. Acidification and its impact on the fundamental carbon and nutrient cycling in the ocean. The biological carbon pump, which can be addressed both from the perspective of the annual net community production in the surface ocean, and then carbon export into the deep sea, and a focus on phytoplankton communities and phenology in the ocean, events like changes in spring bloom timing and so on. There are, in addition, management topics that can be directly addressed by the Biogeochemical Argo program. Living marine resources, we're beginning to understand how to incorporate biogeochemical data into fisheries models and so on, and a biogeochemical Argo program would be the source for real-time data on oxygen distributions and so on that are now used in models that predict tuna abundance and so on. But most of the biogeochemical data that are now used in the model actually comes from other models. And an extremely important topic is carbon budget verification. One of the accomplishments of the SOCAP program is to provide an annual estimate of the ocean carbon uptake, anthropogenic carbon uptake into the ocean. We believe that we can augment that work, greatly improve it by providing full annual cycles of the carbon cycle in regions that are just poorly sampled today, and that the biogeochemical Argo will play a large role in understanding ocean carbon uptake. The ocean carbon uptake is an essential, very essential flux to understand, because that then allows us to understand what's happening on land. Um, so at this meeting, there was a long discussion of what the actual BGC Argo float looks like, and there was agreement that that a core float should carry all 6 of these variables: oxygen, nitrate, pH, chlorophyll A, optical backscatter or suspended particles, which is what is detected, and downwelling irradiance. These are all essential ocean variables. There is a tremendous synergy by incorporating all 6 of these variables onto one float. It extends the scientific questions that you can address. It provides a redundant perspective into some of these questions, and sometimes that redundancy enables fundamental new branches of science to be addressed. By measuring oxygen, nitrate, and pH, we look at productivity from a Redfieldian perspective. They all provide us some estimate of net community production, but we can begin to understand how the phytoplankton population shifts their requirements, their stoichiometric ratios between carbon, nitrogen, and oxygen in response to environmental stresses. We made the point in the paper that these sensors are well tested and understood. We're not proposing a global program with devices and sensors that have not been well tested. Literally hundreds of these devices have been operated for years in the ocean. Papers have been written, and we believe that they're ready for a global program. One of the primary goals of the workshop in Villefranche was to make an assessment of the number of floats that would be needed. The Argo array originally was designed to run at about 3,200 floats. By incorporating other areas of the ocean, the Southern Ocean, and so on. Their target now is really 4,000 floats. We did a number of OSSEs, observing system simulation experiments for the Southern Ocean, OSSEs at the global scale. We looked at reconstruction of satellite data using profiling floats. We looked at carbon and nutrient decorrelation length scales in the ocean, and came to the conclusion that we could make very significant improvements in our scientific understanding with arrays that ranged from 700 to 1,800 floats distributed globally. The mean of all those assessments is about 1,000 floats, and so we've adopted that as our target, an array of 1,000 floats in the ocean equipped with the 6 biogeochemical sensors. Sustaining that 1,000 float array is going to require deploying about 250 floats a year to keep it operational to sustain the 1,000 float population. And that then led to our additional goal, which was to understand the actual operational costs for the system that we're proposing, to come down with a very realistic budget for the system. And that process is sort of recapitulated here. There's a capital cost for hardware. There's the actual lifetime operational cost for the hardware. So you can buy a core Argo temperature and salinity float for about $22,000. The operational lifetime cost, including data processing, the data transmission costs, quality control costs, comes out to be about $33,000. The asterisk down here explains how we come to these conclusions, but it's based on the experience of the community in operating regional arrays in the core Argo system. There was a nice study led by Nikki Gruber adding oxygen to Argo. The capital cost for an oxygen sensor is about $7,000. The lifetime cost of that sensor really totals to $10,000, and so on. You work down. A biogeochemical Argo float is going to cost you about $80,000, but to operate it, it will cost you about $107,000, $110,000 over its lifetime. And So if you are deploying 250 floats per year times $107,000, this is a $26.9 million a year program. Historically, the U.S. in core Argo has done half the floats, and in fact, if you look at biogeochemical Argo, almost exactly half the biogeochemical floats in the ocean today are U.S. deployed. That would make the U.S. share half of this 13 million per year. We believe these are as reasonable and a consistent number as you can get. I think you can go with these as operational costs. These are non-trivial amounts of money, 13 million or 27 million almost per year. That's what it's going to take. So one of my goals in life has been to give a series of public lectures on biogeochemical Argo and what it means in to the layperson in terms, and I always like to kind of bring it down to a level where people can understand the 26 million. So I recently gave a talk at the Halifax Public Library on a Wednesday night in the library. It was snowing. There were like 300 people there. It was great. And I make the point that the operating budget for the Halifax Public Library is $26 million a year. 26 million is not, I mean, as a society, we do all kinds of things for this kind of number. In science, this is kind of a hard number to come by. It's kind of an awkward number. It's, no single program has 13 million available to spend out of the blue, and it's not really quite enough to have a national initiative. But that's what it's going to take to provide a system that really observes ocean metabolism, ocean carbon cycling, provides us the data that we need to really understand what's happening in the open ocean in terms of climate change, which is just something that we are doing a poor job of addressing today. In terms of science budgets, that 26 million, is again not a crazy number. The U.S. deep sea drilling program, 58 million per year. The academic research fleet, just the NSF contribution, 83 million a year. One global class ship in the U.S. at $40,000 a day operating and a target of 250 days is 10 million per year. And the Ocean Observatory Initiative runs at a budget of about 400 million and 45 million a year to operate, which are numbers from the NRCC change report. These aren't crazy numbers, but it's hard to generate them out of a vacuum. So I'd like to conclude. There's a active international planning going on. Again, the web page for the program, biogeochemicalargo.org. There is an International Biogeochemical Argo Steering Committee with representatives from around the world that are involved. There is now a U.S. Biogeochemical Argo subcommittee. It's a subcommittee to the U.S. Ocean Carbon and Biogeochemistry Program. Our first meeting will be next May 23rd and 24th in Princeton with, again, a group of people from a diversity of backgrounds and a diversity of career levels and so on, so that we ensure that we have a broad perspective. And finally, I'd like to make the point that there is tremendous international interest in this. That at the last G7 meeting in Japan, the science and technology ministers met and issued a report, and one of their recommendations: we support taking the following actions: support the development of an initiative for advanced global sea and ocean observation through the global Argo network and with other observation platforms, while fully sustaining and coordinating with ongoing observation. This should include, but not be limited to, increasing the capability of the global Argo network to include more biological and biogeochemical observation and observation of the deep sea. I always have to stress when I show numbers, I do comparable numbers or budgets. I am not advocating getting rid of the deep sea drilling program. I'm not advocating getting rid of ships. I'm just making the point that these are that we should continue to sustain these, that biogeochemical Argo can work effectively in coordination with these programs, but the amounts of money that we spend on those are comparable to what we would need. And so I'm just going to conclude with the last slide that makes the point that we think biogeochemical Argo really is at the crossroads of ocean observing. It interacts with the Global Shipboard Hydrography Program, GoShip. It will interact with the Global Surface Ocean CO2 Atlas Program. It interacts with satellite remote sensing of ocean color and temperature and altimetry and LIDAR, if that comes to fruition. It is synergistic to all of those and provides for satellite oceanography a view into the interior and a view of carbon fluxes that can't easily be observed by satellites. For GoShip, it provides an extension into the interannual variability that GoShip doesn't address well with decadal hydrography, but we need that GoShip data to ensure the calibration of our sensors. And similarly for programs like SOCAT, we can provide a interannual, more highly resolved perspective in areas that aren't well sampled, but yet we depend on SOCAT to provide the absolute calibration perspective. And with that, I think I've done more than my 30 minutes. I'm done.
Thank you very much, Ken. I really appreciate that talk. And Herve, feel free to jump in anytime in responding to questions. So questions are open. There's been a couple asked already. Let me go back to one of the things that you mentioned early on, which is that biogeochemical Argo is now the dominant source of oxygen, nitrate, and pH data compared to ships, with from 3 to 6 times as many profiles. So let me just ask Howard's question first, actually, because it's about that slide. It says that with pH sensors on floats, there's a suggestion in that slide that the pH profiles are not being posted to the GDACs. Why would that be the case?
Compared shipboard profiles, that the data is being posted to the GDACs, Argo, Howard. So if the it's there. That's how I get the numbers that I showed in that table. I went to the GDAC and counted the number of pH profiles that are there.
Maybe Howard can clarify his question. Well, let me.
Could I go back to the slide? Yeah, hang on, Howard. Let's see. More efficient way to do this is. Now I have to guess where that. Okay, boy, lucky guess. Getting close. There. Okay. This is the slide, Howard. So if I go to the Argo GDAC and count the number of oxygen profiles that are available for the year 2016, there are 11,332 profiles, 1,862 pH profiles on the GDAC.
I could add that if you go on the Biogeochemical Argo website, you have a real-time counter that is going to the GDAC. So each day you have an update of the pH and all the 6 variables. So this is.
So I mean, maybe the question is why this data isn't going to NODC, and I can't fully answer that one because at some point this data should show up. Although at NODC I have explicitly only asked for ship profiles when I queried their database. It eventually will make its way into
looks like
NODC
Howard has actually
well.
realized the answer to his question, that there's 2 columns for pH there. Let me come back to just a more general question related to this slide. You also mentioned early on that the number of ship profiles is declining. As we understand more and more about the changes in the biogeochemical cycling of the ocean and how much they might change with climate change, why do you think that number of ship profiles is declining over time?
Um, well, when I gave a seminar recently, and I said, the bottom line is that you first of all you can't get a PhD just by measuring oxygen anymore. You have to go do genomics or iron or something fancier. Of course, there was immediately a student in the audience jumped up and said, "Hey, I just got my PhD by doing oxygen." But in general, I think that we tend now to view in the 80s, oxygen was really that was at the forefront of making ocean measurements, and today, it's sort of an ancillary item that we either don't do or we don't put data into the system when we do it.
And the ship data remains kind of the gold standard for calibrated data. So I know you showed some examples of where you've compared floats to shipboard data pretty favorably. But do you actually use the shipboard data in your quality control for BGC Argo?
Absolutely. So all of the sensors that are used in BGC Argo require a reference database of some sort to calibrate them. And this is true as well in Argo. They do this for salinity. So they have a reference data set that they use to check their salinity sensors for drift and so on. So for oxygen, our reference database is the atmosphere. Okay, so when the floats come to the surface, they make an atmospheric measurement, and we use that. For nitrate and pH, our primary interest is in the upper 500 meters in the seasonal cycles. We create mapped distributions of the GoShip data at depths around 1,500 to 2,000 meters, where there's little or no seasonal cycle, where there's little anthropogenic change. We use the ship data to verify that the sensors are stable, and if it looks like they're drifting, we use the historical ship data at great depth to correct the sensors for drift. So we will have an ongoing dependence for high quality ship data. A good example is pH. We make the sensor better every year, but we look at the 1,500 meter pH data to verify the sensor's operating properly. We can now determine that there in fact is pH drift at 1,500 meters due to ocean carbon uptake, and we need continual updates to the deep pH data to make it really usable. Herve, by the way, Herve's group, they have a nice paper coming out on this very topic, using neural networks to map deep ocean data for quality control of ocean sensor
I will
data.
add that it's probably more challenging to well calibrate sensor for chlorophylls and for oxygen, for example, pH and nitrate, because the reference measurement is needed. It's HPLC measurements of chlorophyll A, but the relationship between the sensor measurement, its fluorescence, and the actual chlorophyll concentration is varying according to community composition, to nutrient status, photophysiological status of phytoplankton. And this you cannot assess with a single measurement at a deployment. So this means that we have also to explore and to invent new methods to address that. We have an evolving calibration in the relationship, for example, between chlorophyll and fluorescence over the lifetime of a float, because the float experiment seasonality in the phytoplankton community composition. So this is, I would say, more challenging for some of the biooptical parameters.
So let me continue on that line of thought and ask you about the sensors a little bit. So how stable are the sensors for the 6 biogeochemical variables? And actually, do you impose a specific model or manufacturer, or is there a wide variety of manufacturers of the sensors?
So we don't impose a manufacturer a requirement. There has been an evolution, towards different technologies. Oxygen is a great example. We started out profiling floats were deployed with electrochemical Clark sensors. The community evolved just because of sensor performance to the fluorescence lifetime optical sensors. There are multiple manufacturers of those particular devices, and ultimately the community maybe will you know, based on performance, select one or the other. But there are at least three different oxygen fluorescence oxygen sensors on floats now, and you know, the actual composition has changed in time. Two types of nitrate sensors being deployed. Right now, only one type of pH sensor. But if somebody, one of the key functions of the biogeochemical Argo steering team is to help provide an avenue for people to introduce new technologies like that. You know, improved sensors, and find a way to you know, keep improving performance of the technology.
Do you publish best practices guides?
There is a biogeochemical Argo. There's an Argo document Herve's group has led on best practices.
Yes,
Herve, I don't know if you want to say.
An evolving, I will say, documentation that is discussed each year as part of the Argo data management team meeting. So since 5 years, the BGC community is attending this meeting. And we have learned a lot on the best practice of Argo. So we are translating progressively this practice and adapting them to the 6 variables. So the level of maturity is varying according to the variables, I would say. pH is just starting, but for example, oxygen is the most mature with respect to best practices. So this is available also. And as part, you can download some of this documentation on the BGC Argo website.
And one other aspect, the SOCOM program is looking into starting a school on, you know, best practices, processing data, how to prepare floats, and so on. And that we may be talking to you, Albert, about ways to fund that. But we would like to run a summer course.
Okay, and while we're in sensors, let me ask Matthew Deaver's question. TNS are presumably included on all BGC Argo floats. And what is the sensor failure rates on the floats?
Yeah, so there's a paper submitted to Journal of Geophysical Research right now, which addresses those questions, including sensor failure rates. So oxygen been incredibly good. We probably have a failure rate in oxygen of about 2%. Nitrate sensors are pretty good. Failure, the recent failure rates are again in that less than 5% rate. pH has been more problematic, and we lose the published number, or the number that hopefully will be published in this JGR paper, is about 5% per year failure rate on the pH sensor. So by the time you're 3 years into a program, you have 85% of your sensors operating. You're losing about 5% a year. That's a little more, that's somewhat comparable to the actual float failure rate, which for the best quality floats is also about 5, maybe a little better, about 4% a year of the floats fail due to mechanical issues. It is annoying when, you know, you add to the 4% float failure, all of a sudden I add now 5% pH sensor failure rate. The pH sensor doesn't impact the operation of the other sensors in the float, but it is just so much more valuable to have them all operating. But if you go on the SOCOM website, for example, it's a program that has 80 floats in the water. We publish our statistics for sensor failures and so on. You can find a web page on there that is sensor stats, and we track that very carefully. We try to be the Toyota of oceanography with continuous improvement. So when we find problems, we try to fix them.
Go ahead, Herve.
I will add that BGC Argo and Argo in general is because of the use of a robotic platform that go at depth most of the time in the dark and with cold waters. This is a natural protection against biofouling for most of the sensors. So sometimes you can face biofouling on some BGC Argo floats, but it's generally because you run them at high temporal resolution, say every day or every 2 days in subtropical areas. Otherwise, we do not face the issue with respect to biofouling, even if the floats stay at sea for more than 4 years. And that is a very nice way, I would say, to be cost effective, because you can use your float and your sensor combination over a long period of time for long time series.
There was one other part of Matthew's question. Temperature and salinity are implicit on the list. That's the core Argo variables. We do that. Everything I showed was in addition to the core.
Let me turn for a moment to the planning for the array, for the biogeochemical Argo array. And you've talked about the major questions that drive it, and you have some work on recommending the number of floats. So let me ask Lisa Levin's question, which is, do you have a way to engage with other entities that can help make the case for BGC Argo? And these are either thematic around, such as the Deep Ocean Observing Strategy that she is co-chairing, the Global Ocean Oxygen Network, GON, which is a new activity for IOC, or the Global Ocean Acidification Observing Network, GOON.
So I would have said 6 months ago we didn't really have a strategy. The plan, Lisa, is that we now have an international steering committee, and that would be a focal point to interact with the Deep Ocean Observing Strategy. In the U.S., we now have just formed a subcommittee of the U.S. Ocean Carbon and Biogeochemistry Program, and that function, one of their tasks is exactly what Lisa is asking. And so, going forward, I think we have a way to address this. We haven't in the past, and as the U.S. committee is just going to meet next month, but that will be an agenda item: is how do we interact? How do we find synergies with other programs and really use that effectively? Because we can't do this.
Let me ask Fred Bigham's question. What happens to BGC Argo floats when they drift into territorial waters? Do you just use the standard Argo notification scheme?
That's correct. So the floats are notified, nations are notified that the floats carry additional sensors, and that they can, if they choose, request to have the additional sensors turned off or the entire float turned off while it's in, doing its thing, but so far that has not happened.
And we have a good question from Fate Shai. So for operational BGC and ecosystem forecasting systems, a higher frequency of data sampling, like a few hours, might be needed. And this is an issue that, of course, operational forecast systems, just for the physics, also face with the regularity of standard Argo profile floats. So what are the issues with that in terms of these 6 sensors and batteries for higher frequency sampling?
Yeah, so the floats are limited by the power they carry. So the type of float I deploy has a capacity for about 250 profiles from 2,000 meters to the surface. And if I want to sample hourly, I would 24 hours a day, 10 days, I'd use up the whole float in a couple of weeks. Our goal right now is to get the seasonal and interannual variability, and so we have opted to go to a 10-day cycle time, which with 250 profiles gives me a lifetime of 2,500 days, which is 7 years for the float. It's the only way right now. We don't have enough money to sustain a dense array, any kind of an array, unless we sample reasonably slowly. So there are people working on making floats that use thermally powered battery systems. eChow has a company that's trying to address this, and there may be ways to do it, but right now with a load of batteries, I can't sample fast, or if I do sample fast, the float will die so soon.
I would complement that. In France and in Europa, we tried to find a compromise between some kind of flexibility in the sampling and respecting the general Argo rules of 10 days, 2,000 meters. So this means that when we have a float with potential of 300 profiles, maybe 200 of them are dedicated to the BGC Argo core, and 100 of them could be dedicated to process studies or to fit with some exploration requirements or some more specific requirements like operational oceanography and data for this net. However, we have to take care, as I said before, that if we increase too much the sampling resolution, the temporal sampling resolution, we might face in warm waters biofouling issues. So it's a compromise also with doing more exploration, but we could face some sensor problem at the end.
So we're almost out of time, but let me ask one last question. Right now, the different national funding sources that are concentrated on the different geographic regions of the globe and the different pilot programs, how optimistic are you that you're going to be able to come, like Argo, to a kind of commitment from different countries for global coverage?
Well, I'm an optimistic person. It's such a good idea. The need is so great. We have to do, and the amount of money is not, I mean, it's comparable to what we do. It will get done. The question is, will it be this year or 10 years from now? And, I'm not optimistic on this year, unless some private philanthropy wants to step in. Maybe I'm not optimistic about the next 3 years after that, but we have no. So as ocean scientists, we believe that climate is going to impact the open ocean. Other than really satellite ocean color, we have in a few time series stations at Hawaii and Ocean Station Papa and so on. Vast areas of the ocean aren't sampled. You could have huge changes you'd never know. Huge advantages to having this data in terms of fisheries management and so on, we believe, and so I think I'm optimistic that it's just too logical a thing not to happen, but will it happen?
I would add that it could be in the same way that Argo has been developed, because initially Argo was a regional project that are well corresponding to national needs. And the second point is, if we want that the BGC Argo develop at the global scale based on the national and regional focus, I think it's very important to develop an end-user community. So when Ken is speaking of training the new generation of scientists, that is basically the end users that will defend over the long term the program.
And just to amplify that, I mean, Argo, the operational oceanography centers, the weather forecasting centers are tremendous customers for the Argo data. We have to find an equivalent committed set of customers for the biogeochemical data. That may be fisheries forecasting. To some extent, that is the physical oceanography models, because the more tracers you put in a model, the better off you are. But we need, beyond science, we're all mostly scientists, but we need a real dedicated operational customer base. People have great ideas for that. I'd love to hear it, but it's nice to have somebody out there that's clamoring for the data.
That's a very good note to end on, and I think it's a very worthy task to try to develop, probably through pilots, to try to develop that user audience, not just a scientific user audience, but a more operational user audience for biogeochemical data. Anyways, let me thank you both. Thank you, Ken. Thank you, Herve, for the talk and for the interaction with the audience. And thank you to the audience members for joining us. And we'll sign off until next time. You can find information about the next webinar in your email or on the Goose website. Thank you very much.
Bye. Bye.
Thank you all.